Good evening. Today's topic is method of induction and binomial theorem. Actually, we use method of induction to prove binomial theorem. See, in mathematics, many times some results are guessed, right? Some results are guessed by observing some pattern and then we prove or disprove them. Consider this. Let us find sum of the first n odd natural numbers. The first odd natural number is 1. Can I write 1 as 1 square? Yes. Then 1 plus 3, sum of the first two odd numbers, 4. Can I write this as 2 square? Yes. 1 plus 3 plus 5. Can I write this as 3 square? So, from this pattern, we can guess that sum of the first n odd natural numbers is what? N square. See, this is not the proof. This is just guesswork. Okay. Consider another example. If I say that 10n plus 3 is always prime, where n is a natural number but not divisible by 3. Take n equal to 1. 10 plus 3, 13. Is 13 a prime number? Yes, it is. Take n equal to 2. 20 plus 3, 23. Is it prime? Yes. I cannot take n equal to 3 because I'm saying n natural but not divisible by 3. So take n equal to 4. 40 plus 3, is 43 a prime number? Yes. Take n equal to 5. 53 is a prime number? Yes. So we are tempted to conclude that 10n plus 3 is always prime if n is a natural number but not divisible by 3. But see, if n is 13, 1, 3, you get what? 130 plus 3, 133. Is 133 a prime number? No, it is not a prime number, right? It is divisible by 7. And therefore, this guesswork is wrong. Again, I'm saying that this is not the proof because here for n equal to 13, we could know that this is not a prime. But in some cases, uh, you come to know that the result is not true for say n equal to 1000 or 1000 plus. So this is not the correct method. Okay. But for n equal to 13 in this case, I can say that the result is disproved. So in this topic, we are interested in the results strictly associated with natural numbers. Now we shall denote the result associated with natural number n by what? P of n. So we will always begin with let Pn denote the result or let Pn denote the statement. We know that a guessed result, GUESSED, a guessed result P of n may be true for some natural number and may be false for the remaining natural numbers. Now we are interested in knowing whether a guessed result P of n is true for all natural numbers. That is, in proving it to be true for all natural numbers n. The method of proving such a result is provided by a principle known as principle of mathematical induction. I repeat, the method of proving such a result is provided by a principle known as principle of mathematical induction. Now in that, what do we do? Let P of n be a statement or result associated with every natural number n. Let me explain first. After this, we will solve or we will discuss one solved example, right? The first step, we verify that the result is true. Which result? P of n. The result is true for n equal to 1. That is, we verify that P of 1 is true. Okay. Suppose first step is over. We verified that P of 1 is true. Then we assume that P of k, in the second step we assume that P of k is true. What is k? Of course, k has to be a natural number. So assuming that result is true for p of k, we prove that p of k plus 1, p of k plus 1 is true. Prove that p of k plus 1 is true. Of course, for that we assume that p of k is true. In other words, we say that p of k is true implies p of k plus 1 is true. Okay, this is the second step. Now, we have already verified what, that the result is true for n equal to 1. So I will put k equal to 1. So if p of 1 is true, p of 2 is true. Is p of 1 true? Yes, we have verified that p of 1 is true. So p of 2 becomes true. Put k equal to 2. If p of 2 is true, yes it is, then p of 2 plus 1, that is p of 3 will be true, and so on. So arguing in this manner, we can say that the result is true for all small n belonging to capital N. Right? So we can say that the proof of proposition P of n by mathematical induction consists of 4 steps. The first step is called as foundation. We verify that P of 1 is true. That is, verify that the given result is true for n equal to 1. Now, second step is assumption. We assume that P of n is true for some k belonging to n. That is to assume that P of k is true. The third step is succession, to prove that P of n is true for n equal to k plus 1. That is to prove that P of k plus 1 is true. And the fourth step is induction. We conclude that P of n is true for all natural values of n. Okay, so this is nothing but the principle of mathematical induction. Let us discuss this solution for the first one rather. Prove the following by the method of induction for all natural values of n. First one, 2 plus 4 plus 6 up to 2n is n into n plus 1. We begin with let Pn denote this statement. Which statement or result? That 2 plus 4 plus 6 up to 2n is n into n plus 1. Can you express this in words? Sum of the first n even numbers is always n into n plus 1. First step, we verify that P of 1 is true. So for n equal to 1, what is LHS? When I say n equal to 1, by that I mean first term, or you can say this is nth term, put n equal to 1, same. So LHS is 2, put n equal to 1 in the right hand side, 1 into 2, 2. Yes, LHS equal to RHS, that is P of 1 is true. Let us assume that for some natural value of k, P of k is true. What do you mean by P of k is true? Replace every n by k, you get the same result. That is 2 plus 4 plus 6 plus dot 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 up to 2k is what? K into k plus 1. We assume that this result is true. Now we prove in the third step, we prove that P of k plus 1 is true. Now what is the meaning of P of k plus 1? Basically, what is P of k? In that we consider first k terms. So in P of k plus 1, we will consider first k plus 1 terms. So tell me how to write P of k plus 1. Logic is simple. First term, second term, third term, kth term. So these terms as they are. And the last term is k plus first term. How to get that? Simple. Replace k by k plus 1. So these terms as they are, k terms, but we have to write one more term. So it is 2 times k plus 1. Right? This is LHS. What about RHS? It is k plus 1. See, uh, brackets are very important. Do not write just k plus 1 into another bracket k plus 2. Okay. So k plus 1 into k plus 1 plus 1. That is k plus 2. Right? Okay, now what is LHS of this? 2 plus 4 plus 6 plus dot 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 plus 2k plus 2 into k plus 1. See, what is the sum? 2 plus 4 plus 6 up to 2k. It is nothing but k into k plus 1. Reason, from 1 we have assumed that result is true for n equal to k. That is why this sum can be replaced by k into k plus 1. But there is one more term, 2 into k plus 1, right? So take k plus 1 common to get in another bracket k plus 2, which is RHS. This means if p of k is true, p of k plus 1 is definitely true. So we can conclude that from above steps and by the principle of mathematical induction, the result P of n is true for all small n belonging to capital N. That is 2 plus 4 plus 6 up to 2n is n into n plus 1 for all natural values of n. Second one, prove using induction 3 plus 7 plus 11 up to n terms is n into 2n plus 1. See, the difference between previous sum and this sum is here we do not know nth term. So first we have to find nth term. Clearly these terms are in AP with first term 3 and common difference 4. So what is nth term? 4n minus 1. Now we say let Pn denote the statement 3 plus 7 plus 11 up to 4n minus 1 is what? N into 2n plus 1. First step, we verify that result is true for n equal to 1. Put n equal to 1. N equal to 1 means first term, which is 3. Or you may say this is nth term. We put n equal to 1. Same thing. 4 minus 1, 3. This is LHS. What about RHS? 1 into 3. 3. Yes. So LHS equal to RHS. That is, result is true for n equal to 1. We have verified this. Now second step, we assume that for some k belonging to n, that is k is a natural number, p of k is true, means what? 3 plus 7 plus 11 up to 4k minus 1 is k into 2k plus 1. Simply you have to replace n by k, that's it. Now on the left hand side, this is what? Sum of the first k terms. Now we prove, we have to rather, we have assumed this. Will you say that let us assume this also? No, you have to prove this. That if this is so, then this is also correct. Now we have to prove that P of k plus 1 is true. That is to prove, we write these terms as they are, 3 plus 7 plus 11 up to 4k minus 1. These are k terms. But there is one more term. How to get that? Replace k by k plus 1. So 4 into in bracket k plus 1. If you open the bracket, 4k plus 4 minus 1. And that is why 4k plus 3. On right hand side also, you have to replace every k by k plus 1. Please do not write this as k plus 1 into another bracket 2k plus 3. You have to put k plus 1 also in a bracket. Now you will ask me why 2k plus 3? Same reason. You have to replace k by k plus 1. So 2 into in bracket k plus 1. So 2k plus 2 plus 1, and that is why 2k plus 3. I hope you understood this. We have to prove this actually. LHS. Now for these many terms, 3 plus 7 up to 4k minus 1, we can directly write k into 2k plus 1, and that is why it is necessary that we write this term. Some students, they write 3 plus 7 plus 11 dot 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 and they directly write this. So you won't get the answer in that case. You have to mention this term. So sum up to these terms is what? From 1 k into 2k plus 1 plus 4k plus 3 as it is. Now just open all the brackets, factorize, you will notice that this is RHS. So P of k plus 1 is true. So from all the above steps and by the principle of mathematical induction, the result P of n is true for all small n belonging to capital N. That is 3 plus 7 plus 11 up to n terms is n into 2n plus 1 for n belonging to capital N. I repeat, you may ask me, sir, why to use this method? Because the terms are in AP. Note that the result P of n need not contain terms either in AP or in GP, right? So this method sum of the first n terms in AP or GP is not applicable in all the cases. Now, third sum, prove by induction 1 square plus 2 square plus 3 square up to n square. We have already discussed this in the topic sequence series. It is n into n plus 1 into 2n plus 1 upon 6. So we begin with let Pn denote the statement or result 1 square plus 2 square up to n square is n into n plus 1 into 2n plus 1 upon 6. N is a natural number. First step, for n equal to 1. What is LHS? 1 square, that is 1. What is RHS? 1 into 2 into 3 upon 6, that is 1. Same as LHS. And therefore, P of 1 is true. Now in the second step, we assume that P of k is true. What is k? Any natural number n. So 1 square plus 2 square up to k square is what? K into k plus 1 into 2k plus 1 upon 6. Right? This is number 1. Assuming that P of k is true, we now prove that P of k plus 1 is true. That is to prove 1 square plus 2 square plus k square. You have to mention these many terms. These are in all k terms. How to write the next term? Simple. Replace every k by k plus 1. Previously it was square of k. Now it is square of k plus 1. On the right hand side also, you have to replace every k by k plus 1. Do not forget to put k plus 1 in bracket. So k plus 1 into k plus 1 plus 1 into 2 in bracket k plus 1 plus 1. So on simplification, you get this. Means we have to prove 1 square plus 2 square plus dot 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 plus k square plus k plus 1 square equal to k plus 1 into k plus 2 into 2k plus 3 upon 6. Now it is LHS 1 square plus 2 square up to k square plus k plus 1 square. Now for underlying terms, what is the sum? K into k plus 1 into 2k plus 1 upon 6 risen from 1 into rather plus this term as it is. Now you know how to add fractions, LCM and so on. K plus 1 can be taken common. Okay. Now what are the factors of this? K plus 2, 2k plus 3. So it is k plus 1 into k plus 2 into 2k plus 3 upon 6. This is RHS. So P of k plus 1 is true. Now in the fourth step, you have to write from all the above steps and by the principle of mathematical induction, the result P of n is true for all small n belonging to capital N. And after that, you have to mention the proved result also. Right now. Yes, so every time you have to write this from above steps and by principle of mathematical induction, P of n is true for all small n. This symbol we already discussed. This is inverted A for all small n belonging to n. 1 square plus 2 square up to n square is what? N into n plus 1 into 2n plus 1 upon 6, where n is a natural number. Sum number 6. Let Pn denote the result or statement 1 into 2 plus 2 into 3 up to n into n plus 1 is n into n plus 1 into n plus 2 upon 3, where n is a natural number. First step, for n equal to 1, what is left hand side? 1 into 2, that is 2. What is right hand side? 1 into 1 plus 1 into 1 plus 2 upon 3, that is again 2. So LHS equal to RHS, that is P of 1 is true. Second step, let P of k be true for some k belonging to set of natural numbers. That is 1 plus 2 plus 2 in rather 1 into 2 plus 2 into 3 up to k into k plus 1 is k into k plus 1 into k plus 2 upon 3. This is number 1. In step 3, we prove that P of k plus 1 is true. That is, assuming P of k to be true, we prove that P of k plus 1 is true. Now, how to write P of k plus 1? Simple. See, these are how many k terms, so we write them as they are. How to get the next term? Replace k by k plus 1. So, k plus 1 into k plus 1 plus 1, and that is why I have directly written k plus 1 into k plus 2. On the right hand side also, I have written directly replace k by k plus 1. So k plus 1 into k plus 1 plus 1, that is why k plus 2. k plus 1 plus 2. That is why k plus 3 upon 3. Now we have to prove this. We begin with LHS. Note that for these many terms, we can directly write this. So this plus this one is this. We have to prove this. Try. LHS 1 into 2 plus 2 into 3 up to k into k plus 1. For these underlined terms, I can directly write k into k plus 1 into k plus 2 upon 3 risen from 1 plus this term. Now I can take k plus 1 into k plus 2 common to get in bracket k upon 3 plus 1 LCM 3. So numerator k plus 3. That is why I have directly written k plus 1 into k plus 2 into k plus 3 upon 3. But this is right hand side. So we have proved that if P of k is assumed to be true, P of k plus 1 is also true. So step 4, from above steps and by the principle of mathematical induction, P of n is true for all n belonging to n. That is 1 into 2 plus 2 into 3 up to n into n plus 1 is what? N into n plus 1 into n plus 2 upon 3. N belongs to capital N. So this was for sum number 6. Tomorrow we'll be solving sum number 7 and remaining sums.